Okay, good morning. We will start. We'll continue our discussion from the point where we left off yesterday. So we had a quick discussion on the various applications of gas turbines, and we found that there are two main applications: jet propulsion. So most of the aircraft engines nowadays use gas turbines, and power generation. And apart from that, there are some other applications like offshore oil rigs, marine propulsion, helicopters, tanks, and some experimental vehicles also have used gas turbines. So let me give you a quick overview of how a gas turbine looks like and how it works. And later, obviously, we will again go through all these components in much more detail. But the idea is that at least at this point, if you are not familiar, you should know the main principle of a working principle of a gas turbine and what are the components, how they look like, so that when we discuss about the cycles, we can relate the processes, individual processes, with the actual components that are present in a gas turbine. Are my slides visible?
Yes, sir.
Yes, sir.
Okay, thank you. So this is a typical large scale gas turbine that you can see here, and it is shown here with half of the casing removed. Okay, so this entire device is put in a casing. Bottom part of the casing is still present, top part is removed. So what we see here are, initially you can see that there is a series of blades like this. So each of this set of blades are mounted on the shaft, and each of them rotates with the shaft. Okay, so these are known as compressor stages. So this first row that you can see here is the first stage compressor. Second row will be second stage compressor, like this. So there are large number of compressor stages. At least here we can see at least 10 to 12 compressor stages. There can be even more number of compressor stages. What is the main role of the compressor? So the ambient air which comes into the turbine, it is at a it is not at a high pressure or high temperature. So the compressor increases the pressure of the incoming air. It is mainly used for increasing the pressure of the incoming air. Why the pressure needs to be increased, it will be clear later on. But that is what is the role of the compressor. Now each of these stages can increase the pressure by a small factor, say around 1.5. So if the inlet pressure is 100 kPa, after the first stage the pressure may be 150 kPa. Okay, so like this. So then the second one will also have a pressure ratio of 1.5. So again from 150 to 225 kPa. So the uh, output of the compressor is measured in terms of the change in pressure that is occurring, or the pressure ratio. What is the ratio of the outlet pressure to the inlet pressure? And this increases in pressure occurs because of how the flow goes through within these passages between the blades. Okay, so this is like a fan. You can consider it's like a fan that is in your room. So the principle is almost similar. In the fan, in a fan, you are providing some power, electrical power, which rotates the motor, and which then pushes the air. So the air goes from one side to the other side, and gains a slight bit of pressure. Okay. So in normal room fans, the blade angles are not very sharp, and number of blades are also low. So the increase in pressure is not very much, not very high. If you consider say large scale industrial fans or even exhaust fans, if you see exhaust fans, there you will see that there actually the pressure change is quite slightly higher than normal fans. So this also, each stage acts like in a similar manner, where you have air which is coming in at a certain velocity and it goes out with a certain velocity, and while going through this section, the pressure gets increased, and the work input comes from the rotation of the shaft. Okay. So instead of electric power, the shaft is rotated by the turbine, and that rotation of the shaft causes the rotation of the blades of the compressor, and which actually compresses the air. So this is the first part of any gas turbine. So then the second part, which is not shown here. Okay. So I will come to the schematic also. So second part is the combustion chamber. So in between the turbine and the compressor, there will be multiple combustion chambers which are spread around in the annular region between the shaft and the casing. Okay. So the air which is say it's an industrial gas turbine. So at the inlet, the air is at normal atmospheric pressure and temperature. So after passing through all these stages, the pressure may be increased by around 20-25 times. So instead of 1 atmospheric pressure, now the pressure can be equal to 25 atmospheric pressure. Okay. So this high pressure and temperature will also increase, obviously, with the increase in pressure. This high pressure, high temperature air enters into the combustion chamber, where fuel is injected and there is an igniter which ignites the fuel, and combustion happens. These fuels are different types of hydrocarbons. Generally, typically, gas turbine fuels or aviation fuels are very similar to kerosene. Okay, means there's some sort of hydrocarbons, and after combustion, they result in carbon dioxide and water vapor. If there is proper combustion, it will result in carbon dioxide and water vapor. And then this, so the in the combustion chamber, the temperature increases dramatically. The temperature of the fluid increases dramatically. The pressure does not increase. It's a constant pressure process because the combustion chambers are open at both sides. So it's not like a piston cylinder arrangement or IC engines where the pressure increases. Here it is open at both sides, so the only the temperature increases, and then the flow goes out from the other side and into the turbine blades, and in the turbine blades, this energy of the means, because the fluid is at high enthalpy, that energy is utilized for pushing the blades in a certain direction, and this all because all the blades are pushed in one direction. This manifests as rotation of the blades about the axis, and this actually rotates the shaft. And the turbine blades and the compressors are mounted on the same shaft. So this rotation of the shaft because of the turbine blades results in transfer of work from the turbine to the compressor. And the work output from the turbine for industrial gas turbines is more as compared to the work input required for compressor. So the excess work that remains in the shaft is transferred to a generator for generating power. We'll discuss a little bit more also here, some more topics. So let us try to take a look at this schematic diagram to get a better understanding of what is happening. Okay. So again, the air comes in at the inlet. Okay. If it is an industrial gas turbine, the air will come in at a very low velocity, means it is just coming in because the compressors are moving and pulling in some air. Okay. If it is a jet engine, then the air will come in at very high velocity because the engine itself is moving through the air at high velocity, and from the reference point of the engine, the air velocity is very high. Okay. So in that case, there will be an additional component which is known as a diffuser, which will be in front of the compressor, and the diffuser is actually like the opposite of a nozzle. So in the diffuser, the high velocity fluid undergoes transformation to a low velocity and dumps its kinetic energy to increase the enthalpy or pressure energy. So the pressure and enthalpy increases and kinetic energy is reduced. So then this fluid passes through this compressor blades, as you can see here. So what will happen is the fluid will pass through the compressor blade, and because the compressor blades are rotating, it will increase the velocity of the fluid. Okay, after it passes through the compressor blades, the velocity of the fluids will increase. And then so the blades which are mounted on the shaft are known as rotor blades because they are rotating with the shaft. So apart from rotor blades in the compressor, there are blades which are fixed on the casing. Okay. So although you cannot see from here, like you can see only one blade on the top and one blade on the bottom, but it will be circumferentially mounted in the annular region on the casing. So these blades which are mounted on the casing are known as stator blades. Okay. So after passing through the rotor blades and gaining velocity, when the air passes through the stator blades, the kinetic energy is converted to increase the pressure and enthalpy. So the velocity of the flow again comes down and the pressure and enthalpy increases. Enthalpy means static enthalpy. Okay, total enthalpy remains constant. Means the pressure and temperature increases, you can see. So again it passes through second rotor stage, again the velocity increases, again passes through second stator stage, again the pressure and temperature increases further, and this keeps on and it passes through multiple rotor and stator stages until the air comes out at high pressure and high temperature. Okay. Typical pressure ratios for a large gas turbine is of the order of 20:1 or 30:1. What is the pressure ratio for steam turbines for large scale thermal power plants? Typical pressure ratio. What will be a typical pressure ratio for steam turbine? You have done power plant engineering course or some steam turbine courses, so you will know. We have solved problems also. Answers?
So 50:1 in that range.
How much?
50:1.
Not really. What is the maximum pressure? Like what were the maximum pressures that we like generally take for a thermal power plant? So what is the pressure in the boiler? You can say maximum pressure after the pumps or in the boiler. Typical pressures that we used to take around 10 MPa, 15 MPa, 20 MPa, right? 22 MPa is the critical pressure of water. So say it is 10 MPa or 15 MPa. And what is the minimum pressure after the turbines in the condenser? What is the minimum pressure in the cycle? What was the condenser pressure?
40 kPa.
It can be 10 kPa, 20 kPa, means it is below atmospheric pressure, right? So if it is say 10 kPa and the maximum pressure in the boiler is 10 MPa, so you can see that the pressure ratio is of the order of 1000. So for steam turbines, the pressure ratio is much higher. Okay, and it is possible there because of the phase change that occurs for the working fluid. For gas turbine, the working fluid does not undergo any phase change. It is always in gaseous state. So you cannot deal with that kind of pressure ratios. Okay. So that is one important thing. And second thing is that these compressors, which increases the pressure with the input of work, generally the work input that is required for compressor is quite high as compared to the work input that is required for the same pressure increase in pumps. Okay, so in steam turbine plants, what happens? The pressure increase occurs in the pump, right? So we have multiple pumps which increases the pressure from say 10 kPa to 10 MPa, and this pressure increase occurs in the pump. In case of gas turbine, the pressure increase occurs in the compressor because you are in a gaseous state. I mean, the working fluid is in a gaseous state. So as a result, the compressors require much higher work input as compared to pumps. What is the basic reason for this? Why the compressors require much higher work input as compared to pumps for the same increase in pressure?
Sir, because of low density of air as compared to water in boiler.
Because of low density of air. Yes. So how does it affect low density of air? Why will low density lead to more work input?
The specific volume is very high, so delta P dot V is very high.
Specific volume is very high. Yes. So specific volume is very high means V delta P, which is the work input, integral of V delta P becomes very high. Delta P, if we keep same, we can keep same, but because V is very high, specific volume, then the work input becomes higher. So your answers are correct, but not exactly to the point. For pumps, the specific volume is very low. So if the delta P is, even if the delta P is same, the work input will be low. But in case of pumps, we generally have much higher delta P for steam turbine. Still, the work input is low. But in this case, the work input is quite high. And as a result, what happens is that a large portion of the work that is generated by the turbine, around say 50%, is used up by the compressor. Okay. So large percentage of the work is used up by the compressor. So compressor design becomes a very important part in this type of turbines. So then the air which is at high temperature, high pressure goes inside the combustion chamber, and fuel is injected. So there may be multiple combustion chambers like is shown here. There can be a single combustion chamber which is annular in nature. Annular means there is a inner lining and the outer lining, okay, with multiple injection points. And there are igniters which ignites this mixture. So typically, the air fuel ratio in gas turbines is kept very high. Means the amount of air is kept very high as compared to the fuel. It is around 50:1, as compared to IC engines where it will be around say 15:1 or 18:1, typically like that. So for hydrocarbons of this type, the stoichiometric ratio is around 15:1, or in that range. Means it is between 10:1 or 20:1 and 20:1. I hope everybody knows what is the stoichiometric ratio, right? So it is the exact amount of air required for complete combustion of the fuel. So in gas turbines, a very large amount of air is passed as compared to the exact amount that is required. Does anybody know what is the reason for that? Anyway, we'll discuss this later on in the course. I'm just curious to see what is your idea on these things. So why the air fuel ratio is kept very high? Can you try to guess?
So it will increase the work output.
Why will it increase
It
the
will,
work?
mass will be high multiplied by the specific enthalpy. It will increase the work.
Not really. So if
So
I
the
keep the amount of
temperature,
fuel same, yes,
so
And
to
for
keep
cooling
the
purpose also,
temperature
sir.
of gas low so that it won't be problem.
it will keep the temperature of the gas low. That is correct. That is correct. So and to answer the first question, first answer actually to clarify, if you increase the air, the work output will not increase because your fuel is same, right? So ultimately the energy is brought by the fuel, chemical energy of the fuel. So if I have very less amount to inject, very less amount of fuel, but keep on increasing the amount of air, the temperature rise itself will decrease, and the enthalpy of the total enthalpy, that is or energy carried by the air fuel mixture, will not increase. Okay, so the volume can increase, but because the specific enthalpy is reduced, ultimately we will not get more work output, because work output will depend on how much energy is carried by the fuel. Okay, so you have to think in that time conceptually. Otherwise, think of what happens. So if I put unlimited air, it does not mean that we can get unlimited amount of work, right? It will depend on the fuel. So the main reason is that if we use stoichiometric ratio, we will discuss this later, so don't worry. If we use stoichiometric ratio, the temperature can go to very high value, like 2200 Kelvin, 2300 Kelvin. For hydrocarbons, this is the maximum, say, adiabatic flame temperature. And this will destroy the turbine blades. Okay. So as a result, we need to keep the temperatures to a much lower value. Nowadays, the maximum temperature still can be quite high, around 1200 Kelvin or 1200, 1300 Kelvin. And if we pass more air, so the mixture becomes diluted and the overall temperature is reduced. Okay. And this has also the added advantage that if the air fuel ratio is high, then more chances of proper combustion is there, means the more air is available, and as a result, almost the entire fuel gets combusted properly. As a result, the combustion efficiency here is much higher as compared to IC engines. So almost 99% combustion efficiency can be around 19%. Means around 99% of the energy that is held by the fuel can be extracted as thermal energy. Okay. So ultimately, after combustion, the combustion products are carbon dioxide and water vapor. And because extra amount of air was present, there will be still excess amount of oxygen and nitrogen. So all this will go out from the combustion chamber, and then there are again stator blades and rotor blades in the turbine. So each turbine stage consists of a stator blade and rotor blade. The stator blades are like nozzles. So once the high temperature, high pressure fluid comes in, it passes through the nozzle and is expanded, and the velocity increases to a very high value. So the high velocity fluid then passes over through the turbine blades, like this kind of blades, and while passing through it, it dumps some of the energy and pushes the blades in the rotational direction, and that manifests as because the blades are mounted on the shaft, that also rotates the shaft. Okay. And again, it passes through another set of the gases passes through another set of stator blades. Again, the velocity is increased, and again it passes through the rotor blades. Again, the enthalpy is extracted, and as a work output for the rotation of the shaft. So this is how it works. And for industrial gas turbines, so typically the work that is generated by the turbine will be much higher as compared to the work input to the compressor. So if the turbine generates 200 kilowatt of work and the compressor takes around 100 kilowatt of work, so rest of the work 100 kilowatt is extracted because it is coupled to the shaft is coupled to a generator shaft, and it is used for generating power, okay, electrical power or whatever power is required. So that is the case for industrial gas turbines. For jet engines, what is done is that for jet engines, the number of stages of turbines are lower. Okay, so it is only sufficient. The number of stages are there so that it is the work output is only sufficient enough to run the compressor stages. So exactly, say if 100 kilowatt of work is required for running the compressor, so 100 kilowatt of work is generated by the turbines. So then the fluid still has lot of energy or enthalpy. It is still at a high temperature and pressure. Then this high temperature pressure fluid is passed through the nozzle of the jet engine, and it accelerates out at a very high velocity. Okay, and this high velocity fluid coming out from the nozzle creates thrust on the engine, which propels the engine and the aircraft forward. So that is the basic idea behind a jet engine. So for jet engines, the turbines, the only role of the turbine is to run the compressor. It is not there for generating additional power. It is just there for running the compressor, and the compressor is still required because you need to increase the pressure, as we will see when we do the cycle analysis. If you do not increase the pressure of the incoming air, and if the incoming air comes and gets combusted and just passes through a nozzle, we will not get any net work output. Okay, because the combustion occurs at higher pressure and the temperature increase occurs at higher pressure. When we do the cycle analysis, it will be clear that that's why we can get additional work output. Okay, so pressure needs to be increased. and pressure needs to be also increased, because then only we can, for industrial gas turbine, pressure needs to be increased, because in the turbine we need a certain pressure ratio to generate the work output. So the fluid needs to be at a high pressure, and the incoming air is at the ambient pressure. And obviously the outgoing air also needs to be at ambient pressure, because you cannot control the outside condition. So the inlet to the turbine needs to be at a higher pressure and temperature. So these combustion chambers have lot of intricate details. We will see later in the second half of the course how the combustion chambers are designed. But where the main problem comes is that, particularly for jet engines, the engines move at a very high velocity. Okay, so the air that comes in also typically is at quite high velocity, and if the combustion chambers are not properly designed, what will happen is that the flow in the combustion chamber will have very high velocity, and the flame will flow out and extinguish. Means if there is a flame, it has a certain flame propagation speed, say 10 meter or 20 meter or 30 meter per second. Okay, if the airflow occurs at a higher speed, what will happen? The flame will tend to go out with the air. Okay, and it will get extinguished. Again, you have to ignite. Okay, as a result, you need to slow down the air so that you can sustain combustion in the combustion chamber. But if you want to slow down the air dramatically, then again there is some pressure loss, which will lead to loss of work output in the turbine. So it's a very challenging task, how to do the mixing and how to. So what is done is, locally there is some low velocity region where the combustion can be sustained, and then additional amount of air is introduced downstream for the mixing to occur. So in a local region, there is a small amount of air, which is known as primary air, which is introduced for the combustion to be sustained, which is introduced at a very low velocity. And more air is introduced subsequently in the combustion chamber, so that until ultimately the entire air can be introduced. Anyway, these things will again be clear later on. I'm just giving a brief idea about how things work. So this compression process, what type of thermodynamic process is this? In general, if I consider it to be a single process, like if we ignore the stages and everything, just for the cycle analysis, if we consider this entire compression to be a single process, what sort of process will it be? Turbine process, what sort of process is turbine process in building steam turbine?
Isentropic.
It's isentropic process, correct? If it is an ideal steam turbine, it's a gas turbine, it's an isentropic process. If there are losses, then the entropy can increase, but still it will be an adiabatic process. Okay, so losses means frictional losses inside. If we ignore the frictional losses inside, it will be an isentropic process. So isentropic expansion process in the turbine is known as isentropic expansion, because the pressure is reduced. The process in the compressor is isentropic compression. Okay, similar to a pump. It's an isentropic compression process. What is the process in the combustion chamber?
Constant pressure heat addition.
Correct. Constant pressure heat addition. So we have three main processes: isentropic compression, constant pressure heat addition, and isentropic expansion. And gas turbines operate with an open cycle, means the fourth process is not present. So fluid comes in at a certain temperature and pressure, then it undergoes isentropic compression, constant pressure heat addition, isentropic expansion, goes out at a certain temperature and pressure. Okay, same fluid is not again recirculated back, unlike steam turbines where the same fluid, which is steam, is circulated again and again. Yeah, it's an open circuit, means the cycle is an open cycle. Okay, so for studying this cycle, we generally close it by putting another constant pressure heat rejection process, and that ideal cycle is known as Brayton cycle, as we will study later in the next class. But in real life, It's just these three processes which are present. Okay. And each of these components we will study in depth later on. We will see that in place of axial compressors, we can also have centrifugal compressors, where the mechanism of pressure increase is different and the flow goes out radially instead of axially. Okay. Any questions up to this point? Any confusions that you have or anything you're curious about?
Sir,
Yes.
you had said that the compression ratio is very small in case of gas turbines.
Yes.
Sir, can you just specify the reason? Like, is it to reduce the velocity or so that?
No. So it is not very low. Means it is not very low overall. Overall, it is around 20 to 30, which is considered to be a very high compression ratio. Typically, when in older days, it used to be around 5:1 or 10:1. Okay. So what happens is that you cannot dramatically increase the. So it's a, there is a huge amount of work input that is required for increasing the pressure in the compressor. Okay, and each stage cannot handle more than 1.5 or 1.4, 1.5 pressure ratio. If I want to increase the pressure ratio to say 50:1, the number of stages that will be required will become too high. And in real life, each of the stages will have its own frictional losses and associated losses, and the weight of the engine will also increase dramatically if you have large number of very large number of stages. So ultimately, from engineering point of view, it is better to have a limited number of stages. Still, the number of stages can become quite high, 12, 15 like this. But the main reason is that a single stage cannot handle more than a certain amount of pressure ratio, 1.5:1 or something like that. So actually, this leads to a very interesting question. Okay, now that because you have asked it, the compression ratio, the pressure ratio across compressor is typically, as I am saying, very low, right? 1.5:1 or even less. Whereas for turbines, which are of similar nature, the pressure ratios for a single stage can be much higher, okay, as compared to a single stage compressor. What can be the reason for this? Each of the turbine stages can handle much larger amount of pressure ratio. As a result, what you can see here is that the number of compressor stages is quite high, but the number of turbine stages is much lower. You can see only 4 turbine stages, whereas the number of compressor stages. So overall pressure ratio may be same because it looks like an industrial gas turbine. So overall pressure ratio may be same, but only 4 stages are needed for the same pressure ratio of say 20:1 or 30:1, whereas so many compressor stages are required. So what can be a reason? Fundamentally, if you think, what can be a reason that compressors cannot handle very large pressure ratio and turbines, each turbine stage can handle very large pressure ratio? Any idea? So what happens in a compressor? The flow velocity is, so ignore the flow velocity. Okay, what happens when the flow is going from one side to the other side? Pressure is increasing or decreasing? Overall, pressure is increasing. Okay, and the flow has to go against the increasing pressure. So against adverse pressure gradient. Typically, when we consider normal flow, it happens when the, like, from high pressure to low pressure, right? In the compressor, the flow is going against the pressure gradient. It is going from the side of low pressure to the side of high pressure. Because of the additional work input, this is this is possible, but the flow is going against the adverse pressure gradient. So as a result, if there is very large pressure gradient, there will be flow separation, and which will lead to large amount of losses. Okay, large amount of mixing and large amount of losses will occur. Whereas what is happening in the turbine, the pressure is decreasing, right, from the upstream side to the downstream side, and the flow is actually going along the pressure gradient, not not against the pressure gradient. So flow is going in a direction in which the pressure is decreasing. As a result, it is a favorable pressure gradient. So even if we have a larger pressure drop, then also because the pressure gradient is favorable, there is less chances of flow separation, and we can, each stage can be designed with a much larger pressure ratio. Okay, so this pressure ratio which is generated typically depends on the blade profile, as we will see later. So you will be able to see, it's not very clear from here. These blades are actually much more twisted, the turbine blades. So large amount of change in angle occurs in the turbine blades as compared to the compressor blades are not twisted at all. Means it is very less twisted. Okay, it will be twisted as you can see, but very less twisted. So the more is the twist, more will be the change in the velocity, and more is the actual change in the pressure. So if the turbine blades can have this kind of very twisted profile, because there won't be any flow separation because the flow occurs along the pressure gradient. But if you had put similar profiles here, there would have been flow separation and caused dramatic reduction in the efficiency of the compressor. As a result, you cannot have very much twisted blades. As a result, the pressure ratio is much lower. Is it? Yes.
The twist in the turbine blades, it is to compensate for the axial velocity change, right? Velocity of the blade. Axial change in velocity of the blade.
Not really. The twist is there to actually increase the means it is there to increase the axial velocity. Sorry, it is there to decrease the axial velocity. So in the nozzle, the fluid comes in with a very high velocity, and not the axial velocity. Sorry, axial velocity remains same. So the overall velocity. So overall
Radial
velocity.
component.
Yes. So what? Not radial. Radial is the outside direction. So
Yes.
it is the tangential component. Okay. So the flow comes in. It is, you can consider it like a bucket, right? So the flow comes in at a high velocity. So I think I will have a certain picture also later on. This we will discuss later. There is no nice picture, but what happens is that the flow comes in at a certain angle and it goes out from in another direction at a certain angle. And because of this change in direction, if the change is more, what will happen? The change in momentum in the tangential direction, will component of momentum, will be more. As a result, the blades will gain more momentum and it will move with more force. There will be more force that is exerted on the blades if it is more twisted. So you can just consider it to be like shaped like a bucket or a inverted U, like a U shape. So the flow comes in, hits it, and flow goes out from the other side. Because the flow hits the blade moves forward. Okay. So more the change in direction of the fluid, more will be the momentum transfer to the blades, and more will be the work output. That is the reason it is twisted. Is it clear to you?
Yes, sir.
What is the time? Okay. Any other questions? Anything? Anyway, these things will be discussed later in much more detail. But I hope this gives you a feel of how the gas turbine works. Okay. So we may get some more interesting points, remember more interesting point later on. I don't remember everything right now, but while we go through the detail description, we can come up with some more interesting questions. A lot of things are actually quite interesting in this type of devices. Anyway, so before we start with the before I start with the actual course, let me give you a brief history of how the jet engines have developed. Okay, so that you can get an idea. And jet engines were for the first devices that use gas turbine properly. So it is good to know the history of jet engines. Okay. So the first type of prime movers that were developed, or the first type of engines that were developed, you guys might know, is were the steam engines. They were developed towards the end of the 18th century and became quite popular in the 19th century. So steam engines were engines where the working fluid was steam, okay, and these were reciprocating steam engines. These were not steam turbines, reciprocating steam engines like your say petrol engine or diesel engine, somewhat similar in nature, but instead of internal combustion, the combustion was external. So these were external combustion steam engines, okay, EC engines, not IC engines. So what used to happen? So there were large engines where the steam was expanded and basically the steam forced the. So there was it was like a piston cylinder system only, and the steam was generated by using coal in a outside furnace, and these were very popular. Of course, you might know these were very popular for railways. So in the 19th centuries, railways become very popular and used steam engines, and the fuel was manually provided. So there would be a person who is standing there with a shovel to just shovel the fuel, shovel the coal in the combustion chamber or the furnace, and that will hit the steam, and that steam will move the piston and generate the power. Okay, so this became quite popular in the 19th century. So after that, towards the end of the 19th century, the first two types of engines were conceived. So first was the IC engines, or instead of steam engines or coal-based engines, the first type of internal combustion engines were developed based on Otto cycle and then subsequently using diesel cycle. Okay, and they became quite popular for automobiles during the earlier 20th century. Okay, so 1900, around the turn of 1900, and at that time, steam turbines also were developed. Okay, steam turbines also got developed, and steam turbines got quite popular for uh, power generation. So the first aircrafts that were developed, uh, the first aircrafts properly came to usage during the First World War for military purpose. Of course, at that time there were no civilian aircrafts, and the first aircrafts were at that time it was very complicated, right? So because just a few years back only automobiles have been developed, and then there is a big jump because aircraft is much more complicated device. So the first aircraft engines were similar to automobile engines and used to look like this. So this is known as a rotary engine. Okay. So how this works? So all these were like diesel engines, individual piston cylinder, which were mounted on a shaft. Okay. And the shaft was bolted with the aircraft fuselage or your aircraft chassis, and the rotation that was generated resulted in the engines rotating at a very high velocity. Okay, so the shaft was fixed and all the engines rotated at a very high velocity, and a propeller was mounted on the engines itself. Okay, the propeller was mounted on the engines, so the propeller used to rotate with the engines at a high velocity and generated the thrust. Okay, propellers like this. Okay, so similar to this. So this became quite popular during the First World War, but they had severe limitations. Okay, so why this became popular was that means at that time there was another concept apart from this, the concept of radial engines. This is rotary engines. The other concept was radial engines, where the pistons were fixed, piston cylinders were fixed, and cylinders were fixed, and the shaft rotated. So cylinder was fixed with the chassis or the aircraft fuselage, and the shaft used to rotate, and the propeller was mounted on the shaft, which looks to us nowadays, it looks like a more logical design. But at that time, during the beginning of, say, invention of aircraft, this type of rotary engines had more advantage as compared to this radial engine, because cooling was a very important requirement at those times because cooling was not as efficient as now. So for rotary engines, the cooling was much better. Okay, air used to pass through all this at high velocity because they were rotating. Much better cooling was there, and like it had lot of another practical advantage was that it acted like a large flywheel. So as a result, the power output was much more uniform. Okay. However, this had a very big disadvantage, practical disadvantage. As a result, their operations were only limited to a few hours. Okay. What was the main disadvantage? All these piston cylinder arrangements, even say your IC engines or any IC engine, will require some lubricant so that the piston can move smoothly in the cylinder. So many of you may be using bikes or scooters or cars. You know that you have to pour lubricants. Otherwise, what will happen? Because of very high friction between the piston and cylinder, the movement will become very restricted and it can break the piston also or the crankshaft also. Okay. So always there should be some lubricant that is passed inside because otherwise the piston will not move smoothly in the cylinder. So for this rotary engines, the main problem was that when you pass the lubricant because of very high centrifugal action, it was very easy for the lubricant to pass from one side to the other. You do not need a pump also because just because of centrifugal action, it will pass from one side to the other. But it is not possible to bring back that lubricant again to the central region because of these very large centrifugal forces. So that lubricant was basically wasted. So what happened was that lubricant was used up for the combustion process itself. Okay. But at that time, it was not a problem because these aircrafts were designed only to last for a few hours. So a single, because these were used for aircraft raids, and each aircraft raid would last 2 hours, 1 hour, 2 hours like this, short distances only. After that, even if the engine goes down, it's fine because these were more like at that time it was more like a single-use type of aircraft. Because in First World War, you can imagine the aircrafts were in a very primitive stage. And the power output was also very low, so typically less than 100 kilowatt. So gradually, with much more improvement, the radial engines became more effective. Okay, it did not have that problem of that lubricant cannot be recirculated back, and the cooling also improved, and the power could be improved dramatically. And typically, around Second World War, radial engines were the most popular engines and used typically could generate around 1,000 kilowatt of power. Okay, this is a typical radial engine where each of this is a piston cylinder arrangement. So each of this is a cylinder, and the combined work is transferred to the shaft. The shaft rotates and the propeller is mounted on the shaft. This is a typical Second World War aircraft, okay, which used this type of engine. So the first civilian aircraft that were developed also used these radial engines. Instead of a single radial engine, they used multiple radial engines because the aircrafts were quite large inside. This is a very old aircraft from the 1950s. You can see that this is very old aircraft by looking at the windows. All the windows are square windows. Nowadays, you know that we don't use square windows because of stress concentration. So initial aircraft designer did not know that stress concentration can be a very critical factor. So square windows were used, and there were a couple of accidents because at the corners of the windows there was very high stress concentration, which led to failure of the fuselage. So nowadays you will not see any sharp edges in the windows. The windows are rounded off. Okay. So anyway, so these used radial engines. So radial engines were very widely used around 1940s, and were used widely for this World War II aircrafts, okay, by many of the countries. So around that time, two groups were. Have we run out of time? Almost run out of time. Two groups were independently working on use of turbines for jet propulsion. Okay, so turbines were already known, were used for steam turbines were already in use, but two groups came up with the idea of using gas turbines for jet propulsion. So one of the groups was a German group working with the scientist von Owen, and they developed a design like this. This design is almost similar to the design that I have discussed with you in today's class. There is a series of axial compressor. I can see 3 stages here, and then there will be some combustion chambers which are not shown here, and then here you can see couple of turbine stages. Okay? And then there is a nozzle through which the fluid is accelerated. So this type of design was generated towards the late 1930s and early 1940s and became quite popular. Similarly, parallelly in UK, another group working with Frank Whittle, they also developed independently these jet engines. Their design was somewhat different. They used a centrifugal compressor. Centrifugal compressors are different because in axial compressors, the flow occurs axially. In centrifugal compressors, like centrifugal pumps, the flow comes in axially but goes out radially, okay, in the outside direction. So then you have to again move back the air towards the combustion chamber. So you have to move the radial air in the axial direction. Okay. So as a result, this looks different. So, and the cross-sectional area is more. So at that time, this also became quite popular, and aircraft were developed based on both these designs. Nowadays, we follow all of the aircraft follow this von Oehlen's design because of lot of advantages. Because in axial compressors, the cross-sectional area is less. As a result, it leads to less drag, and drag is a very important factor in aircrafts. Okay. And basically, the flow is always aligned along with the shaft. In centrifugal compressors, the flow has to be moved again back in the axial direction, and it leads to more complication. So this is not the actual engine. This is just a prototype to show you how the engine look like. This is one of the actual engines from like the time of von Oehlen. So quickly it was found that jet engines have a better power to weight ratio as compared to IC engines. For the same output of power, the IC engines used to have a very large weight. So the jet engines for the same weight could deliver much more power. Okay, so the power output was much higher, and this became quite popular. And after that, gradually there were various types of jet engines which were developed. The first type was turbojet. Then we developed something called turbofan, and parallelly turboprops were also developed. I think we will continue this discussion in the next class, and then we will jump into the cycle design. Okay, so we will stop here, and from the next class, next week, we will start with the actual calculations and actual mathematics. I will finish this introduction, and we will have a quick look at what is turbojet, what is turbofan, what is turboprop, how they look like, what are ramjets and scramjets, and basically these engines. And later on, we will revisit them when we study them in much more detail, each of the engines. Okay. So what are the advantages, disadvantages of turbojets? All of them are still widely used. Turbojets are used for military aircraft, turbofans for large passenger aircraft, and turboprops are used for small passenger aircraft and helicopters. So we will see why this happens. So let us stop here. I will download the attendance from directly. Okay. Any questions?